Hello differential equation students. In this video, let's take a look at how do we solve Cauchy, Euler differential equations. So this is one of the non-linear differential equations with non-constant coefficients. In generally, we say a differential equation which is of the form something like this: a n x to the nth derivative of y, some constant times x to the n minus 1 times n minus 1th derivative, a1x times dy over dx, first derivative a sub 0, y is equal to g of x. If you pay attention here, the first derivative coefficient is some constant times x to the 1, right? And the n minus 1th derivative coefficient is x to the n minus 1, and the nth derivative is the coefficient of the nth derivative is x to the n. So you have this x to the n, x squared y double prime, x cubed y triple prime, x times y prime, and so on would be the usual form. So for example, here's an example. If you take a look at this example number 1, you see that x squared is the coefficient of the y double prime, x is the coefficient of the y prime, and y is by itself. And if you take a look, y triple prime comes with x cubed, x squared goes with y double prime, x goes with y prime, and just the constant with that. So again, these are constants. These are our a n minus 1, so on. But here's that is the key, right? So if you have this form, we call this the Cauchy differential equation. We solve this method using a substitution method, and that substitution method is called the Cauchy-Euler Cauchy-Euler method, or Cauchy-Euler method. And what is the substitution? The substitution is basically this right here. We'll talk about in a moment what that is. So before we go, let me give you the overall scheme of how do we solve this Cauchy-Euler differential equations. The way that we are going to solve the Cauchy-Euler differential equation is the following. So what you have is, you have a differential equation, right? You're going to have a differential equation y in terms of x, right? You're going to have a differential equation y in terms of x. Then what you're going to do, you're going to transform this to a differential equation of y in terms of t. Then once you do that, then you're going to solve that differential equation. So then you're going to have a solution to the differential equation y in terms of t. So you're going to have a solution y of t. And then what you do is that then you do the resubstitution. When you do the resubstitution, then you're going to have a solution y as a function of x, right? So that is what you're going to have. So you have y as a function of x, a differential equation. Then you transform this into y as a function of t, and that transformation is basically this right here, which is x equals e to the t, right? And then you work with that, and then of course the derivatives are going to change. We'll see how the derivatives are going to change in a moment. Then now you have the differential equation, right? Now you have the differential equation y as a function of t, right? Then what you do is that then you solve it. Usually what happens is that when you solve these things, usually what you get is you get the higher order linear differential equations with constant coefficients. We know the methods already how to solve them, so you're going to use the methods that we learned earlier to solve them. And then once you solve this, and then you do the resubstitution, and the resubstitution is t is equal to ln of t. That resubstitution is t is equal to ln of t. That's something that I've highlighted in here, right? That's what we're going to use: the substitution, resubstitution, and so on. Then you're going to have a solution, and that solution is going to be a solution to the original differential equation, which is the Cauchy-Euler. So here is the solution to that differential equation right there, and that's how we solve, and that's the usual process. So a couple of things in here. When you go from when you do the substitution, right, remember the initial differential equation is y is a function of x, right? The initial differential equation is given to us as a y as a function of x. So now we are going to the substitution, right? Now you're replacing x as a function of t, and that function is e to the t in here. So now eventually you're going to have y as a function of t, and that's what this differential equation is going to be. Now how does that process works? But before I go that, let's take a look at one small quick thing. How does the chain rule works? That will be useful for us, our discussions. So you all know the let me just make this smaller. All right. So if you take a look at the chain rule, right here, what you have here is we have you know, y as a function of y is a function of x is given to us, and then we are changing that as a function of t. Now what I have here is, you know, y as a function of x and x is a function of t. So if you want to find the dy over dt, because that's what this differential equation here is going to be, right? So you know by the chain rule, this is going to be dy over dx times dx over dt. So therefore, if you say what is the dy over dt, right, by the chain rule, you would know that this is going to be, you know, dy over dx multiplied by dx over dt, right? So therefore, I'm going to say this is dy over dx times dx over dt. You all know this very well. And by the way, while I'm here, let's take a look at what is the dy over dt, right? Let's take a look at what is the dy over dt in here. If you dx over dt in here, the dx over dt, right? The dx over dt, the one that I have right here, because x is a function of t, right? X is a function of t. So the dx over dt in this case would be, it's e to the t, and that's by itself, right? So it's going to be x. So ladies and gentlemen, what I have here is, if I go back in here, what I have here is I have this dy over dt equals dy over dx times x, right? In other words, what I have here is dy over dt is equal to x times dy over dx. I want you to pay attention to this. We'll come back to it in a moment, right? So that's what we have. So we're going to, that's the kind of a thing that we're going to use when you transform this differential equation y as a function of x into a y as a function of t, right? The differential equation y in terms of t and y in terms of x and so on. This is what we're going to use. But before I go that, I want to quickly, you know, look at some notations in here. We're going to use for, you know, we have been using dy over dx, right? Whenever we have the only one variable, dy over dx, we are using this as a dy, d as the operator. Here this d means the derivative with respect to x, right? So for our purposes from now on, for this particular section, whenever we write this dy, right, regular d with the y, that means the derivative with respect to x. The variable here is, the independent variable here is x. If I use a script to d, that means that is the derivative is with respect to t. The variable here is t. So for example, if it says d squared y, the regular d, so therefore this is a second derivative with respect to x. This is script to d squared y, that means the second derivative is with respect to t, right? Second derivative of the y with respect to t. So I want you to be careful on this. There are some other notations that you might see in some books, and those are the followings, and that's perfectly all right as well. You might see this in some books, might say, you know, dx of y to denote dy over dx. That kind of tells you, you know, what that is. Similarly, you might also see this is the dt of y. That means the derivative with respect to t of the function y. So there's going to be, you know, dy over dt, and that's perfectly all right as well. But we're not going to use those notations. We're going to only use this. We're going to only use the script d, a regular d, and a regular d, and the script d is what we're going to use for our purposes. Now let's take a look at how does the transformation, what is the relationship between the derivative with respect to x and the derivative with respect to y. What is the relationship between this, this and this? As a matter of fact, we just looked at it already here, but I'll come back in a moment. We're also going to take a look at the relationship between this and this. And in generally, can we find a pattern of the nth derivative of y with respect to the nth derivative of t? So our goal is, in the next few minutes, our goal is to see what is the relationship, right? What is the relationship between this nth derivative of y with respect to t and the nth derivative of y with respect to t. What is the relationship between these two is what we are going to take a look at the next few moments. All right, having said this, let's take a look at in here. So if I use my notations, ladies and gentlemen, you would agree with me that this is a script d, right? That's a script dy, and that is equal to x times the regular dy. What do I mean by that? This is the derivative with respect to t is equal to x times the derivative with respect to x. And that's what we just did, right? We just did earlier from this calculation. That's what we got. Now let's take so which means we found the relationship between these two, this and this, right? This and this. Now let's try to figure out the different relationship between this and this and see if we can find a pattern, and then eventually generalize it to the nth derivative, something like that. All right, let's take a look at the second derivative, right? With respect to let's take a look at the second derivative with respect to t. So let me write that down. So what do I mean by that? I'm going to write down the in symbols. I'm writing that as the script d squared of y. What does that mean? That means this is d squared y dt squared. You all know that very well. Now what does that mean? This means the derivative of the function with respect to t of the first derivative of the function with respect to t, right? All right, so remember, my goal is to find the relationship between these two, correct, with respect to y and the t. And now I am going to rewrite this, right? I'm going to rewrite this into something else, which is this d over dt of, dy over dt. If I borrow this right here, I'm going to borrow this right here. If I borrow this right here, ladies and gentlemen, what I'm going to have is, if I borrow this right here, what I'm going to have is, I'm going to have, let me change the color. I am going to have x times dy over dx. There's a small issue in here. That issue is that what I have here is a function of x, but I'm supposed to do the derivative with respect to t. So for that, what I'm going to do, I'm going to use the chain rule here again. If you use the chain rule here, ladies and gentlemen, what I am going to have is the following. If you use the chain rule in here, so what I'm going to have here is d over dx of x dy over dx times, using the chain rule, d over dy over dx over dt, not dy, dx over dt, using the chain rule. So now if I simplify this, all this, ladies and gentlemen, what I am going to have when I simplify all this, right, you would agree that I am going to have the following, which is, I'm going to use the product rule in here. So it's going to be dx over dx times dy over dx, right, plus x times d squared y over dx squared times, right, dx over dt. But we already know what is the dx over dt. The dx over dt is equal to x. So I'm going to simply say this is times x right here. And now if I simplify this, this is going to be 1. This is going to be 1. So therefore, this is 1 times dy over dx plus x times d squared y over dx squared. I'm going to distribute this x with this and this x with that. When I do that, you would agree with me that I'm going to have x times, and this is going to be x squared. So if I rewrite this in terms of my notations, because the script d and the regular d, you would agree that I'm going to have, this is x times, this is the regular dy, and this is x squared, and this is a regular d squared y. And what is the x dy? If you recollect what we had earlier, x dy is equal to script dy, right? So x dy is equal to script dy. So I can rewrite this, if you don't mind, as the script dy plus x squared d squared, that's regular d, right? dy d squared y is equal to script d squared y. And if I simplify this, ladies and gentlemen, what I'm going to have is, I'm going to have a script d squared y. I'm just grouping all the scripts d's and the regular d's. dy is equal to x squared d squared y. And so therefore, now if I try to simplify using the operator notations and then whatever we discussed earlier in terms of the annihilators and the operators, this would be script d of d minus 1 of y is equal to x squared d squared y. In other words, what I have is this is x squared regular y double prime, or if you want to say this is x squared d squared y over dx squared. So now let me try to combine what I have so far. If I combine what I have so far, what I have is this d script dy. Script dy happens to be x times dy. What do I mean by that? This means, in other words, what I have is dy over dt is equal to x times dy over dx, right? And the next one, which is x squared d squared y over dx squared, which in other words is x times d squared y, x squared d squared y is going to be d of d minus 1 of y. And can I extend this? Yes, I'll let you do this on your own. I can extend this. If I extend this, right, in generally I can say, let me go show you the cubed one. X cubed d cubed y would be script d minus 1 and d minus 2 of y. So if I extend this, right, to the x to the n dn of y, that is going to be script d minus 1. You keep on do that until d of n minus d minus n minus 1 of y, and that's what it's going to be. So what we are going to do, ladies and gentlemen, we are going to make use of this information right here. We're going to make use of this particular information right here, and then we are going to plug this back into the differential equation and then solve it. So let me summarize what I just have right here. So if I summarize what I have, what I'm going to have is this x y prime, which is the regular x regular dy, which is going to be script dy, and this x squared y double prime is going to be x squared d squared y. Regular dy is going to be script d of d minus 1 of y. This x cubed y triple prime is going to be x cubed regular d cubed y is going to be script d minus 1 of script d minus 2 of y. So in general, if I extend it, what I'm going to have is x to the n, nth derivative of y is going to be x to the n dn of y, which should be script d minus 1 script d minus 2 dot 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 script d of n minus 1 of y. And that is what we are going to use to transform the differential equation from here to here. So what we are going to do, we are going to use all the information that we have right here, right? We are going to convert this differential equation in terms of y of x into this, and then we solve this, and then we are going to use the resubstitution, and then we get the solution. So let me show you one example of how to do this process so that you kind of understand what I am going to do. Let's take a look at this problem. X squared y double prime minus 2xy prime minus 4y is equal to 0, with x being positive. Alright, let's see how do we solve this. So as I said earlier, the method we're going to use this, right, is to transform from here to there, and then there to here, and then there to there, right? So now what do we have is here we have differential equation as x squared y double prime minus 2xy prime minus 4 equal to 0, with x being positive. So let me rewrite this so you kind of understand what this equation really means, right? So this is the differential equation in terms of x, right? So this is the differential equation y as a function of x. So if you write it for clarity, this is x squared y double prime of x minus 2x y prime of x minus 4y as a function of x is equal to 0 on x being positive, right? Now we are going to transform this to a differential equation in terms of
t. But before I do that, let me write down in terms of my operator form. This is going to be x squared regular d squared y minus 2x regular dy minus 4y is equal to 0. So I'm not going to write down as a function of t and so on, but I hope you'll follow. When you look at the symbols, you should be able to differentiate between, I don't want to use the word differentiate, distinct between the x and the t. Let's see how do we do that. So now we are going to use this, the substitution. So this is the this is step 0, you want to call it. The very step 1 is the substitution step, and that substitution step is the following, which is x is equal to e to the t. When you do that, then you know that this x times d becomes a script d, and x is squared, d squared is going to become d of d minus 1, and so on. But we only have second derivative in here, so we can stop it right there, because all we have is a second derivative is all I have, right? So this is going to be replaced by this, and this is going to be replaced by that, and then we're going to work on. So now what I have is, when I do the substitution, ladies and gentlemen, my second step, I am going to have the differential equation, now y as a function of t, and then what happens, that y as a function of t, let me use a different color, is going to be, now this is going to be transformed into script d of d minus 1 of y, here y is a function of t by the way, minus 2 script d y is a function of t here by the way, minus 4 times y of t is equal to 0. I'm not going to do that next time, but you kind of follow along what I'm doing. Now let me simplify this. From now on, I'm not going to write it as a y as a function of t. I think whenever we use a script, it's understood that it is a y as a function of t. So if I simplify this, let me rewrite it down. I'm going to rewrite it down as this is a script d of d minus 1 of y minus 2 d of y minus 4 y is equal to 0. If I simplify this, this is going to be d squared y minus dy minus 2 script dy minus 4y equal to 0. Further simplification tells me this is script d squared y minus 3 script dy minus 4y equal to 0. What has happened is something magical has happened. What do I mean by that? If you did not pay attention earlier, all I have here, I have a non-constant coefficient. Thanks to this substitution, this differential equation y as a function of t, now I no longer have variables in here. I have constant coefficients. All I have is constant coefficients. So now, which means I can use the method that I have used earlier. So, which is solving higher order linear differential equations, what I call whole deck, right? Solving higher order linear differential equations with constant coefficients. When you do that, the very first step that we do is, finding the characteristic equation. When you do the characteristic equation, this is going to be m squared minus 3m minus 4 equal to 0. And right, and that tells me the solution to this one is going to be, if I factor this out, this is m minus 4 times m plus 1 equals 0. So m is equal to negative 1 comma 4. And so therefore, our fundamental set of solution is going to be e to the negative x and e to the 4x. Is that right? No, it's not right. I made a mistake in here. What is the mistake? This is not a function of, these are not functions of x. That's wrong, because now our variable is t. So therefore, this can be functions of x. So some of the mistakes that we usually do, so don't do that. These should be t's. These should be t's. So e to the negative t and 4t right there. So therefore, the solution for this one would be in terms of t, right? As y of t is going to be c1 e to the negative t plus c2 e to the 4t. So where we are. If you go back, we are right here. If you go back, we are right here. We have a differential equation in terms of y of x. We transform this into a differential equation in terms of y of t, and we are right there. Now we have a solution y in terms of t right there. That's all we have. Now we're going to do this as resubstitution back and then get that. So if I do that, let's see what happens. what we are going to have is, now this is our next step, right? Step 3. Let me go back to the blue again. The step 3. Now here I'm going to use, t is equal to ln of x, or you can say, x is equal to e to the t. Either way is okay. Then if you do that, then this is going to be y as a function of x, no longer t now, c1 e to the negative ln of x plus c2 e to the 4 times ln of x, which is, by the way, c1 e to the ln of x to the negative 1 plus c2 e to the ln of x to the 4. E and ln are inverse of each other, so this is going to be c1 x to the negative 1 plus c2 x to the positive 4, and that's a solution, y as a function of x. We are right here in our process. That solves this particular problem, and that's how this is the basics of in solving this problem. There are some formulas if you want to take a look. I mean, that's perfectly all right. You can use them if you don't want to from here to there. If you want to, once you have these m's, there are ways that you can directly write this is a solution in terms of this, and that's perfectly all right. Let me again, there are more things that are in your book you can follow. Let me give you those. If you want to use that formula, you can do that. And also I want to say a few other things here. What if the roots are repeating? What if you have complex roots and so on? It doesn't matter. You're going to use the same way you did earlier. The only thing is that you're going to use this, t is equal to ln of x and then x is equal to e to the t. But it gets complicated in terms of, it's not really complicated, but some of you it might be a little intense in terms of algebra there. So if you don't want to go through the algebra, although you should, here are some nice way to do, and that is if you have real and distinct. So these are shortcuts if you want to. So if you have two roots, right, let's just say m1 and m2, if they are real and distinct, right, that means they are real and distinct. If they are real and distinct, what you have is you're going to have m1 is not equal to m2. Then the solution, the fundamental set, right, I'm going to say the fundamental set in terms of x, fundamental set in terms of x would be e, usually it's a e, right, it's not a e in this case, it's going to be x to the m1, x to the m2, right? That would be your fundamental set in terms of x. What if you don't have real and distinct? What if you have real and repeating? Right? What if you have real and repeating? If you have real and repeating, then what you're going to have is, you have real and repeating. That means we have m1 is equal to m2. Then your fundamental set is going to be x to the m, and then you're going to have x to the m times ln of x, right? What if you have imaginary complex roots, right, with the imaginary numbers? Then what you're going to have is, if you say roots are alpha plus or minus I beta, then the fundamental set is going to be x to the alpha cosine beta times ln of x inside the cosine, and then you have x to the alpha sine beta times ln of x right there. So we can use this also to do that, but make sure you know how to apply this. I will do another example in the next video that basically I'm going to solve this problem, right? In the next video I will solve this problem. This is a linear, third order linear differential equation with non-constant coefficient, which is also non-homogeneous. So let's see how to do that in the next video. That's all I have in this one. I will see you in the next video.